Molecular formula. This is the actual ratio of atoms in a molecule, unlike the empirical formula, which is the lowest whole number ratio, which may or may not be the actual ratio. The molecular formula is the actual ratio of atoms in a molecule. So the empirical formula, again, is the lowest whole number ratio. The molecular formula is the actual ratio. And so again, for example, if you had, I don't know, let's say C2H4, it would have an empirical formula of CH2, but its molecular formula would be C2H4. So the lowest whole number ratio is the empirical formula. The actual molecular formula is C2H4, so we call that the molecular formula. Realize something like methane, its empirical formula and molecular formula are the same thing. So its real formula, its molecular formula, is already in the lowest whole number ratio. Therefore, its empirical molecular formula are the same. So do ionic compounds have molecular formula, you're probably wondering? And as you know, ionic compounds, since they are already in the lowest whole number ratio, that is what the formula is for an ionic compound. This is why we don't need prefixes when naming them. They are already in the lowest whole number ratio, and therefore all ionic compounds, their formula unit, the definition is, that's the lowest whole number ratio. So all ionic compounds are given as empirical formulas. That is what an ionic compound's formula is. So the molar mass of any compound will be a multiple of the molar mass of the empirical formula. We sometimes call this the empirical mass or empirical molar mass maybe, but the molar mass itself of the actual formula will be some multiple of the empirical formula's molar mass. If they're the same thing, like methane, then their molar mass and their empirical mass will end up being the same thing. But if it's a lowest whole number ratio that's been scaled down, then it will be less than that, and the molar mass will be some multiple of that empirical mass. So if we know the empirical formula and the actual molar mass, if you have those two bits of data, then you can actually find out what the actual molecular formula is. So often we will have some way of measuring the actual molar mass of the molecules themselves, get the weights of the molecules themselves. Then we can break them down and find out the percent compositions of them, which you know from percent composition we can get the empirical formula. So from there we can put the two pieces together and get the actual molecular formula and find out what the molecule actually is. So the first thing to do is to divide the actual molar mass by the empirical molar mass to see what the ratio is between those two molar masses, the real molar mass and the simplest ratios molar mass. This factor is then going to be applied to the empirical formula, and then you'll know what the actual molar mass is. So, for example, if you have benzopyrene and you find out that its molar mass is 252 grams per mole, so that's the actual mass of a mole of those molecules. We could also get the empirical formula from some data like the percent composition. So then the question is, okay, well, what's the actual molecular's formula, the actual molecule formula for this particular compound here? So what we can do is we can divide the given molar mass of the compound by the molar mass of the empirical formula. So the molar mass of the given compound here, which is the real molecule, and then we can find the molar mass of the empirical formula, the lowest whole number ratio of its formula, and we can get the molecule's formula from that. We're going to round to the nearest whole number. Hopefully we're very, very close to a whole number once we get this through. So again, take the actual molar mass, calculate what this would be. So we've got 5 carbons, we've got 3 hydrogens, add them up together and we'd end up with 63.07. And so that is the molar mass of the lowest whole number ratio. This is the molar mass of the real ratio. So if we divide the molar mass of the real ratio by the molar mass of the empirical formula, we see that the empirical formula is 4 times too light, or the real formula is 4 times heavier than the empirical formula is suggesting. So then we know what to do with that. We take the empirical formula and we multiply those amounts by 4. So if the empirical formula was 5 carbons and 3 hydrogens multiplied by 4, and this gives us the actual molecule's formula. So another way of going about this is that if you have a molecular formula, you don't have to go through the empirical formula. You may or may not have the empirical formula, but if you have the percent composition and you have the molecular formula, that's really all you need too. So you can actually skip the empirical formula and go right to the real molecules formula as long as you have the molecular formula and the percent composition. How we do that is, again, if we have the molar mass of the compound, and if we're given the percent compositions, essentially we just need to say, okay, well, here's the molar mass, the mass of a mole of it. So if we found out 4.79% of it is hydrogen and 95.21% of it is carbon, we can apply those percentages directly to the molar mass to find the molecular formula. So we do this by, again, using that molar mass. We assume we have 1 mole. If we did have 1 mole of this stuff, then it would weigh 252 grams, right? Because a mole of it weighs 252. That's the molar mass. So then we can apply those percentages of the carbon and the hydrogen to that 252. What is 95.21%? Remember, this is the percentage written as a decimal. So we're dividing it by 100 to put it back into decimal form. And so what is 95.21% of the 252 total grams of the actual molecule itself? Because that will be the amount of carbon. And what is the 4.79% of the total here? And that will be the amount of hydrogen. So we run that calculation through and we see that, okay, well, of this total mass here, 239.93 grams of it is carbon and 12.07 grams of it is hydrogen. And see what we have here, right? We've got a mass ratio. We're looking for the actual formula. So if we convert these to moles, we'll have the mole ratio, and that is the formula. So that's easy to do. Take your mass, set up your conversion factor, grams on the bottom so they cancel out, moles will carry through. So we have 19.98, pretty close to a whole number there, moles of carbon. We have 12 grams, and convert again with another conversion factor over of hydrogen over to moles of hydrogen. And again, moles will carry through, and that's pretty close to a whole number. So essentially what we're saying is this formula here has about 20 moles of carbon to about 12 moles of hydrogen. That's the formula. So we can write that in. Again, we don't want to have it at a decimal place where numbers are always going to be off by a little bit. As long as we're rounding within 5%, we should be okay with that. And so our formula is going to round to be C20H12. That is the actual formula of the molecule. And again, we're doing that using not the empirical formula, though we could do it, but we can actually apply those percentages directly to the molar masses, convert to moles, and then we'll have the actual ratio.